This video is going to cover the solution for 8.5-14. Now this problem is a combined loading problem, and I am going to go into a fair amount of detail in actually solving this problem. So I'm going to do just part A, but I want to go through kind of start to finish, going from the beginning of this problem all the way through that solution of part A. And this is going to be a longer video because I want to talk about some of the combined loading issues and concepts and kind of expand on them so that hopefully it will help you understand it in more detail. So with that, let's get started from our problem. So 8.5-14 says a post having a hollow circular cross section supports a load acting at the end of an arm that is 1.5 meters long. The height of the post is 9 meters. The section modulus is given for the cross section of that. Assume the outer radius of the post is 123 millimeters. The inner radius is 117 millimeters. Part A says calculate the maximum tensile stress sigma max and maximum in-plane shear tau max at point A on the outer surface of the post along the x-axis due to the load P. Load P acts along line BC. Okay, so there's a lot of information there that we need to unpack. Basically, if we take a look at this, we have a cantilevered beam. This cantilevered post, basically it's supported at one end. It goes up, it has a support that's going horizontal, and then there's a force at the end of that. So this force, what we want to recognize is that this force is going to be creating a reaction, or it's going to be creating a reaction down here at A, or it's going to be causing stresses to occur down here at point A. Now they've identified what point A is, and we'll kind of highlight that here in just a minute. But let's start going through all of the information as given. So first thing we need to know is that P is 3.2 kilonewtons. P is equal to 3.2 kilonewtons. Okay, let me make that 3 there. It's acting at the end of this arm. The section modulus is S, and that is given as 2.65 times 10 to the 5th millimeters cubed. And it is given the radius here. So we've got R2 is equal to 123 millimeters, and R1 is equal to 117 millimeters. Now we do have our drawing, so I'm going to redraw that so that we can have that here. So I'm going to put that right here. So here is our post, here is our crossbar, and then we have our force P acting here. And so if we are consistent, this is point A down here, this is point B up here, and point P points to a point C right over here, and I'm going to draw this on here as our coordinate system, X, Y, and then straight up here is going to be our Z. So we have all of that. Now I'm going to draw a couple of other things on here. So point B here, we really want to know the coordinates of that. So best thing to do, let's just say, so X is going to be 0, X is going to be 0, Y is going to be positive 1.5 meters, and the height is going to be 9 meters. Okay, so we have that coordinate. We'd also need the coordinate for point C, and they give us that. So it's minus 3.2 meters to, I'm going to draw it down here actually. Let's do this. Let's make it down here. So we've got minus 3.2 meters, 2.5 meters, and 0. Okay. So we have that. So now we basically have our problem all set up. We know what we're given, and we're given our problem here. So really what we're being asked for is the maximum tensile stress and in-plane stress, shear stress at point A. So we're really looking at what is going on down here. So where do we want to get to? Well, we want to figure out the stresses that are occurring at point A. Now, at this point, what we need to recognize is that this force P is and we haven't looked at it specifically yet, but when we just kind of look at it cursory here, it's really three-dimensional. So we have an X component, we have a Y component, we have a Z component. All of these can be placed at A. So we can replace force P at A, and we can also look at those forces are going to be creating moments about point A. So we're going to need to come up with forces and moments that are acting at point A. Basically, this is, if you remember back to our statics, this is a simplification of a force system onto a given point. So that's really what we're doing here. So calculating the forces and moments. Once we have these forces and those moments, then we can take a look at those and determine what stresses are going to be occurring at point A. So at this point, we could kind of anticipate what's going to be happening at point A as far as stresses, but really we're just going to be looking at these forces and moments. And once we have those identified, then we can actually figure out what are those stresses. And that's ultimately what we're trying to get to. So we're going to go from forces, moments to stresses. And so this is ultimately where we want to go. So let's start with our forces and moments. Now, before we get started with our forces and moments, we need to take a look at what's given. We're given the force, we're given the section modulus, we're given the radius. Now, we can see that a lot of this is given in millimeters. Now, this is kind of a personal preference, how you want to work through these problems. Personally, I like to convert all of my units to our standard SI units, which would be in meters. I know that a lot of people like to work in millimeters. If you like to work in it and you feel comfortable about getting the right answer, the right conversions, go for it. But I tend to want to convert these. So my radius is here. 123 millimeters is 0.123 meters. Our one is 0.117 meters. The other thing that we need to do is convert our section modulus, and we need to convert our section modulus. So for converting millimeters, we need to convert to meters cubed. So we're going to be multiplying by 1,000 cubed millimeters cubed. So this is 1 meter cubed per 1,000 cubed millimeters cubed. We can multiply that up and we get our new section modulus to be 2.65 times 10 to the minus 5th meters to the third power right there. So now we have that in our standard SI units. Okay, so now that we have that, let's go through and start working on these forces and moments. So I'm going to break this down. Now, I assume that you, at this point, would be able to do all of this and these next few steps, but I'm just going to step through it just so I can kind of show it for completeness for you if you're still having difficulty breaking some of this down. So what we're going to do is first we're going to break down force P into its components here. So really what we're going to do is the first thing we're going to do is figure out this position vector B to C. So our vector B to C, and our vector B to C, we need to look at our point C minus our point B, or our coordinates, and we're going to end up with, so our X is minus 3.2 minus 0, and our Y is going to be 2.5 minus 1.5, and our Z is going to be 0 minus 9, or we can write this out as our vector of minus 3.2i plus 1j minus 9k. Okay, so that's just our position vector. We're ultimately wanting to get to the unit vector here, so we need to know the magnitude of BC. So we're going to do this, and we know that we need to square root this. So this is going to be minus 3.2 squared plus 1 squared plus minus 9 squared. Oops, there we go. And when we do that, we get, and I'm I've got these calculated out already. I just plugged this into my calculator, but 9.604. So I'll try to save a little bit of time here. So we've got our magnitude, and now to get our unit vector BC, we take BC divided by our magnitude of BC, and we can basically take our vector here, divide each one of those by this, and we're going to get our final solution here. I'll just write it out. 333 I and plus 0.104 J minus our, let's see, so this is actually, should be a minus right here too. That first one should be negative, the last one should be negative, so 0.937 K. So now we have our unit vector. Now that we have our unit vector, we know the magnitude of the P, or the force that's being applied. So our force, our equivalent force at A, so F, and I'm going to write this, F at A is going to be equal to our unit vector, or our scalar load, times our unit vector in the BC direction. And when we do that, basically we take our 3.2 kilonewtons, multiply by this vector, each one of those terms, and we end up with a vector of minus 1.0662 kilonewtons in the I direction, plus 0.3331 kilonewtons in the J direction, minus 2.9987 kilonewtons in the K direction. So we have our I, J, and K. So now we have all of our forces, or our force vector that we have there. Now those forces are going to be translated to be acting at point A. That's what the thing that we want to do. So the other thing is that we need to figure out the moments. Now, the moment that's created at P, we want to know the moments about point A. So we need to come up with our, let me see, I'll draw this on here with this color. We have our radius vector. And when we have our radius vector, we can say the moments about point A is going to be to the radius vector, cross product with our force vector. And I should put this force vector right there, just like that. Now to calculate this up, we know our force vector, we just need to know our radius vector here, and in this case our radius is between A and B, and B is A is 0, 0, 0, so this is relatively easy to figure out. So we just need to set up our determinant. Remember, so we're going to set up our determinant, I, J, and K. Our radius vector goes on the next line. So here the radius vector is 0, 1.5, and 9. And then we have our force vector, so our I, J, and K components, or minus 1.0662 and 0.3331. And our minus 2.9987. Now remember, all of these are in kilonewtons here, and these are all in meters there. So we have our consistent units. I didn't put them in here, but we can go through here, solve for our determinant, and we get our final moment vector. And I should put that vector notation here. So moment about A is going to be equal to, and I'm not going to go through the solution for the determinant, but we get the final solution of a negative 7.4696, pardon me, 96 kilonewtons, and I'm going to put this in there, kilonewtons meters in the I direction, minus 9.5958 kilonewtons meters in the J direction, and then a positive 1.5993 kilonewton meter in the K direction. Okay, So this is a lot of just setup. Now remember, this is basically just our statics and that we need to do to get into this problem. Again, we're looking for the forces and the moments. And we have our force here, we have our moment here, and that is all about our point A. So we can take this force acting at that point and replace that with these two forces acting, or these two, the force and the moment acting at point A here. So I want to talk a little bit more about this because this is where it seems pretty, we should have a good concept of it, but I want to show it just so that you have a better feel for what's going on at point A. So I'm going to draw this out this way. So I'm going to put down, this is going to be our kind of our point A right here, and I'm going to draw our coordinate system. So this is in the X direction, this is in our Y direction, and we have our Z direction. Okay, Z here. And then if we take a look at our cross section, so our cross section right down here, this is our hollow tube. So if we draw that cross section on here, okay, just the very end, not the whole tube, but just the very end of it, this is going to be our point A as defined in the problem. Point A is on the outer surface of the post along the x-axis. Okay, so along the x-axis, outer surface right there. So that's the point that we're ultimately looking at. But basically, these forces are going to be really acting about this point across this kind of entire cross section here. So let's take a look at what does this force mean. So in the I direction, we have a minus 1.0662 kilonewtons. So really, we have in this direction, we have 1.0662 kilonewtons. So I've drawn it in the negative x direction. So I've gotten rid of the negative sign, but it's pointing in that direction. So we need to be careful with the directions of our arrows that I'm going to be drawing on here. The next one is a positive in the J direction. So that's going to be in this direction, in the Y direction, and this is going to be a positive 0.3331 kilonewtons in that direction. And then our final is the K, which is in the negative direction. So it is pointing downward. And this is minus, and I don't need the minus because I've drawn this, so this is going to be positive here. So this is going to be 2.9987 kilonewtons. So those are the forces that are acting on point A, or at least this cross section here. So that's the translational forces. We needed the rotational forces or the moments. So now we can look at these guys here. So at moment about point A in the I direction. Now remember, that's in the X direction. We have a negative 7.496. Now if we look at this, remember we use our right hand rule. So our x-axis is positive in this direction, so we put our hand there. So a positive moment is going to be going this way, but we have a negative moment, so it's going to be going this way. So I'm going to draw this on here. So it's going to be drawn on here like this. So about that axis, we're going to have a negative moment, or a moment in the negative direction, and that's going to be 7.496 kilonewton meters on there. So we have that moment acting about point X, our axis X, our x-axis. If we look at our Y, we have a negative acting about that one. So again, if we look at our y-axis is in this direction, positive rotation this way, but it's negative, so it's going to be going in the opposite direction. So we're going to have a rotation going this way, and that is going to be 9.5958 kilonewton meters. And then finally, we have a positive k direction, or moment about the k-axis. So if we look up our k-axis, it's going straight up, rotating it this way. Our moment is going to be acting about our axis this way, and it's 1.5993 kilonewton meters. Okay. So I know that this is a little bit confusing, or it may be a little confusing, but we have our cross section, our point that we're interested in. We have our coordinate system acting here. We have all of our forces that are linear forces and our rotational forces that are acting on this cross section. Now, this is where it gets, this is now where we go from our forces and moments to our stresses. Once we can draw this out, it makes it a little bit easier to visualize going from our forces and moments to our stresses. So the thing that we want to do when we look at our stresses, there's a couple ways to approach this, and I'm going to do it one way. It's not necessarily the only way to do it, but it's one way that I'm going to help try to explain where we're getting these stresses and where are they acting on this section here. So the thing that we need to recognize is that we are looking at point A. Point A is only one point on our entire cross section. So what I want to do is I want to draw, I want to take a stress cube that's right at point A, okay, and I'm going to put it right like this. So this is kind of our infinitesimal stress cube. Well, that's pretty small there. I'm going to redraw it so it's a little bit bigger over here. So let's do this. So I'm going to draw this on here. Okay. So now here is going to be, so if we think of this, this is really our point A. Our x-axis is here. Our y-axis kind of goes all the way back to the center, so our y-axis and then our z-axis, but our z-axis and y-axis directions are really the same here. So our z direction is going upwards, our y direction is going in this direction. And then our cross section, okay, so this is just one part, this is our hollow cross section, you know, it's just, again, I'm just kind of making this a little bit larger so we can see this stress cube, because we really need to identify the stresses that are occurring here. So let's take a look at this. So if we think about the stresses, we have a stress in the x direction, we have a force in the x, a force in the y, a force in the z direction. If we take a look at this, our force in the z direction, let's start there. This force is acting downward, and it's acting in an axial direction of our hollow tube. So this is really going to create an axial stress or a axial stress, and we can call that, maybe we'll call that just sigma z. And how is that going to be acting on our stress cube here? Well, it's going to be acting down on this top surface, and that's going to be our sigma z. Now, don't get confused. Maybe I'll call this sigma zf, just so that we know that this is due to the force in the z direction. So that's going to be the stress that force is going to create. How about let's start back with our force in the x direction. Okay, so what is this force? What stresses is that force going to create? Well, if we look at this, this is not necessarily a direct shear condition. There's no force acting on this face, so there's no sigma, you know, a compressive force acting on that face. So we might have a shear stress. So in this case, we might have a shear stress due to bending on there. And if we think about that, so we have a shear stress going in this direction. And if we take a look back, we can look actually back in the book and where they talk about this. And in this case, remember, this goes back to this is back in chapter 5. And I'm going to just flip a few pages here just so that we can see this again. So remember our chapter 5. Here we talk about shear distribution of shear stresses. Okay, so this is a rectangular cross section, but remember when we have those shear forces in a beam, the stresses at the top and the bottom are zero. So remember, the force is acting downward here. So when it's acting perpendicular to the neutral axis, the shear stresses are zero at the top, zero at the bottom, and maximum in the midplane or at the neutral axis. So if we go back to our problem here, in the F direction, or in the X direction here, A is really at the top or the bottom, however you kind of decide on that cross section. So that force, and actually, or that stress in a cross section like this would be at that top point, or it's at this bottom point here. Because our shear stress is, so if we orientate this maybe in this kind of way so that we can see that our cross section here, or maybe if I orient it in this manner, maybe this will make a little bit more sense. So point A would be right here. Our force is in this direction. That has 0 shear force on it. So basically, if we force X is going to cause zero stress. Now, if we take a look at the Y direction, we can do exactly the same thing in the Y direction, but now if we look in the Y direction, the point A is on that neutral axis if it was bending about the centroid of that cross section. But the force is in there, so A is actually going to have a maximum shear force. So, or a shear stress, I'm sorry. So we're going to have a shear stress due to the bending. So I'm going to call that tau bending. So basically, it's the bending of the beam, but it's actually the shear of it. So that is going to be calculated here from chapter 5. So out of these 3 forces, we can see that we have 2 stresses that we need to take into account. Now we also have our moments. Moments X, moments Y, moment Z. Oh, and before we get to our moments, where is this shear acting? Well, if we take a look at our shear stresses, and we need to go back to kind of our beams here, our cross sections, it shows it in the book on how this shear force is going. So the shear force on this cross section, the force is in downward direction. That vertical face has that shear on it. Okay, so if we're thinking about why it's going in this direction, that shear is acting on this top face. So it's going in this direction. So this is going to be tau B. So, and then basically because of that, this face is going to have our tau B, okay, because we need to have it balance out just like this. So that's the face that shear stress is going to be acting on. Okay, so that takes care of our forces. Let's go to our moments. Let's talk about our moments now. Now, when we look at our moments, we are going to have a couple things. Let's take a look at our moment in the X. Okay, so this is bending about the X-axis. So we're rotating this section about the X-axis. Well, again, if we look at the bending about the X-axis, A is on the neutral axis. And in bending, and if our point A is on our neutral axis, there is 0 bending stress or axial stress associated with that. And in this case, there's no shear stress associated with that rotation or that bending in there. So moment in X provides no stress here. Y, if we look at the bending moment there, the neutral axis is this way, and our point A is at the extreme fiber end. So we are going to get a sigma, an axial force, or an axial stress due to bending at point A. Now, where does this occur? Well, since this beam is kind of bending this way, it's trying to stretch. It's going to try to stretch or put point A in tension. So it's going to be acting on this top face again, and it's going to be pointing upwards. And I'm just going to just draw this here. So it's going to be pointing upwards, opposite of our other one. And this is going to be our sigma B right there. So that's our next stress. And then finally, we have our moment about our z-axis. Well, we have our moment about z-axis, and what's that trying to do? It's really trying to twist. It's trying to torque this. It's trying to rotate it in plane. And what is that? Well, when we rotate in plane, that takes us all the way back to our chapter 3 in our torsion. Okay, so we're going to be dealing with torsion here, torsional stresses. So in moment Z is going to create a torsional stress and torsion. Now, where does this occur? Where does that stress occur on our stress cube? Well, if we need to kind of go back and look, they give us some hints in here. It's not necessarily the clearest on where that all falls out. But if we take a look at our stress square here, it doesn't, there's no stress on this outer surface, outer face. They're only on the inside faces. So actually, this stress due to our torsion is acting in this face right here. So again, in the same direction as our other shear stress that's acting on there. So we've got our tor that's acting on there. Okay. So now we've gone all of our forces, moments and linear forces, to our shear stress, or to our stress cube, our three-dimensional stress cube. Now, a couple things let's point out on our stress cube that we have so far. So what do we have? We've got two forces, two axial forces acting on this top face, our sigma ZF and our sigma B. And then on our shear stress, in this direction, we have two forces, our tau B and our tau due to a torque, and that's acting on those two faces. So the nice thing with this now is we know what stresses we need to solve for. And that's ultimately what we need to get into to be able to figure out our sigma max and our tau max. Now they talk about in-plane shear. Okay, so the maximum in-plane shear stress here. So how are we going to calculate this up? Well, this is a three-dimensional stress cube, and we want to go to two-dimensional stress plane. Essentially, the shear stress is acting in this plane. It's kind of the YZ plane. So what we're going to do is we're going to take this cube, and we're going to make it, and we're going to split it like this, and that is going to become our stress square that we have. So now if we take a look at this, we can draw this in a planar sense, and we can show all of these forces on here again. So we have our sigma ZF going compression. We have our sigma B acting in tension, and then we have our shear stresses on here. So maybe I'll draw the shear stresses on this face just to make it a little bit easier, so that we have our tau B, and we have our tau torque due to our torque on there. And really in this, what about the stress here? And this would really technically be considered our sigma y. That would kind of be in this direction, sigma y. Sigma y, there is no sigma y. There is sigma y is equal to 0. And if we even take that to this point, well, what about this sigma x? Sigma x on this face. There is no sigma, there's just no stress acting on that face of that stress cube. So both of those are 0. We're going to, since they're both 0, the maximum in-plane shear stress is going to occur where we have shear stress occurring. So that's why we're going to take this plane versus one of these other planes in on that stress cube. So this is going to give us our maximum. So once we look at this, we can combine these up into a single axial stress. We can combine these up into a single shear stress, and then we can do our Mohr circle to get to our sigma max and our tau max. Okay, so we're going to talk a little bit more about that, getting to that point right here. So the next thing is calculating up these stresses. So we've already got the roadmap for what we need to be able to calculate up. So let's take a look. We'll start off with our forces here. So sigma ZF. Sigma ZF. What's the equation for our sigma ZF? Well, this is an axial force. So basically an axial force, a compressive axial force, is going to be calculated up by force divided by area. And in this case, all we need to do is come up with our area, and we know our radius. So this is a hollow circular section. So it's pi times r2 squared minus r1 squared. And so we can take this, remember R2, I'm going to put it in meters. Okay, so I would write this out as pi as 0.123 squared minus 0.117 squared, and that's going to be in our meters, and then we can plug that into our calculator and we get 4.524 times 10 to the minus 3 meters squared. So we have that, and we need our force. So basically our force is from our z direction, so this is going to be 2.9987 kilonewtons divided by our area of 4.524 times 10 to the minus 3 meters squared. Plug that all in, and we end up with a 662.9 kilopascals. Now remember, we got kilonewtons, we got meters, so we're going to have a kilopascal in there. Now, the thing that we didn't, we need to watch here is that I've converted these. So this was really a negative force into a positive force with an arrow pushing down, which means that this is in compression. This is a compressive axial stress. So that takes care of this stress right here, sigma ZF. So the next one, sigma B. Sigma B. And sigma B is due to a bending stress about the y-axis, or a moment on the y-axis. And we can go back and take a look at the equation for this. Is that this is our stresses in the beam sections. This is back in chapter 5 also. MC over I, but we are given our section modulus, so it's really M over our section modulus. And in this case, remember, there is a sign associated with this. We're going to just kind of figure that out, kind of looking at the problem. And we kind of did that already a little bit earlier here, in that we said the moment is going this way, and it's really putting that stress is going to be creating a tensile stress at point A. So we're not going to deal with the plus or minus signs on there. We just know that we're going to calculate this up and come up with a tensile stress. And we know the equation was M over S. And in this case, the moment is 9.5958 kilonewton meters divided by our S, which we have 2.65 times 10 to the minus 5 meters cubed. And we can plug all that in, and we end up with a stress of 36,210 kilopascals, and that is in tension. So we have our two forces here. So again, we have our two axial forces, and we want a total. So we're going to say this is going to be our sigma Z total on here. Well, we know that we're going to be subtracting these from one another. Tension is our positive, compression is our negative, so we're going to add these. So we're going to say 36 minus 210 kilopascals minus 662.9 kilopascals, and we end up with an overall of 35. Well, actually 35.55 megapascal. So we can actually do that. So that's going to be 35.55 megapascals. Now, once we have that value, we can go on to our shear stresses. So we need to go and calculate our two shear stresses here. So the first one is, let's figure out our tau B. tau B, and this is the shear due to our shear stress in that beam. So again, we can go back to our chapter 5, and chapter 5 has, let's see here, here it is. So actually on this page here is the maximum shear stress in this cross section. We use the VQ over IB, or in this case for a hollow circular cross section, we can use this equation. So we can say this is going to be equal to 4V over 3A times R2 squared plus R2R1 plus R1 squared over R2 squared plus R1 squared. So we can plug all of those values in to get this shear stress. Now, once we have, we know all of these, we know the shear. Remember the shear, we can come back over here. This is in the y direction. So this is our V in this case is going to be equal to our 0.3331 kilonewtons. We plug this into here. We calculated our area before, and it's in our standard meter notation. So we can plug everything in, and once we do that, we end up with 147.2 kilopascals for tau B. So we're left with just one more to calculate up, and that is our torque, or our shear stress due to our torque. So in this case, we need to go back to all the way back into chapter 3. Oops, chapter 3. And if we take a look at our equations here, our tau max is going to be equal to T, our torque, our distance to our point, and then IP. So for a circular cross section, we need to look that up. We can look it up in the back of the book. We also have it listed here in the book too. So basically we have our torque due to torsion is equal to TR over IP, and we need to know that IP is going to be equal to pi over 2 times R2 to the fourth minus R1 to the fourth. So at this point, we know all of this. We know R2, we know R1, we know our torque. Our torque is our moment about about Z here, which is our 1.5993 kilonewtons meters. So we just need to calculate up this. And our R, the R here is the maximum, that's the outer fiber, so that's really R2 is our that gives us our max, which is the point that A is on. So we can plug this in, we can calculate up IP, we can plug IP into here, plug R2 in, we know T, we can then calculate up our shear stress due to our torque. Oops, let's try that one more time. Shear stress due to our torque is equal to, let's see here, plug that all in, and we get 3,017.8 kilopascals. Again, we need to combine these two up. So we're going to get our total torque, our tau total. And in this case, both of those shear stresses are going in the same direction, so we can add these together. So we add this one, and we add this one, and we end up with 3.165 megapascals for our solution. Now that we have those, we have our axial force, we have our total shear force, we can apply it to our in-plane stress. So here we can redraw this, and we have a axial stress in the Z direction, which has 335.55 megapascals, and we have a shear stress of 3.165 megapascals. And remember that shear stress acts there. This normal stress, again, is 0. So now we have our stress cube that we can then figure out our maximum shear stress, maximum principal stress. Remember, for this, we can do this with Mohr's circle. So if we do that with Mohr's circle, we can do this with our sigma, and our tau is in the negative direction here. So we can look at this face. It is a 0, sigma is 0, and our tau is 3.165. So this is going to have some point right here. And then our second face, which is going to have our 35.55, and we're going to go up to get our 3.165 megapascals. So we can then draw our line for our Mohr circle. We have our center. We can then draw our Mohr circle here, and we find that this point is our sigma max, and then we have our distance here, which is our tau max, and those are the two values that we are going to solve for. In this case, you can go through and plug that all in, and it's going to turn out that we get our sigma max is going to be equal to 5.83 megapascals, and then our shear tau max is going to be equal to our 18.05 megapascals on there. So that's going to be the solution to part A of problem 8.5-14. Hopefully that helps. If you have any questions, please let me know.